today we are going to generate this model on an A4 piano note. Let's record it. We can see it pop up in the time domain. This is the discrete time domain. We also see it pops up in the frequency domain. This is the discrete frequency domain. We get between the two using the discrete Fourier transform. Now, we can kind of see some stuff going on in the time domain. We can see it kind of gets louder here and then softer and then louder and then softer. And we can see that it's definitely made up of sinusoids. Which ones? It's kind of tricky to tell. Well, maybe we can go to the frequency domain and we can see more information. We can see that there's spikes every so often. This indicates a nice, pleasing musical sound, either harmonic or near harmonic. But if we zoom in a little further, we're going to see that it doesn't really tell us much. In fact, this is the absolute value of our frequency spectrum. So in reality, this would be three-dimensional to account for phase shifts. That does make it hard to see. In fact, that makes it impossible to see some stuff. But what we're noticing here is that just looking at the time domain, just looking at the frequency domain, the information is hard to see. It's there as long as you don't take the absolute value, but it's hard to see. So we're going to perform this procedure to turn this into a more intuitive model, a more robust model that we can do all this analysis and manipulation on. So I'm gonna have it begin by setting up a wavelet decomposition, a Gaussian wavelet decomposition. It's gonna ask us what is the fundamental frequency to search for, 440. It wants us to know how many bands do we want to generate, how many harmonic bands. And it's around 10 here, so we'll do 10 harmonic bands. Now what it's going to do is it's going to search for each one of these peaks. And it's going to do so using the string harmonic dilation equation. I'll show that in the comments below. So it finds up here the first harmonic and it isolates it with a Gaussian filter. And then the contribution shows up down here, 438 cycles per second. All right, let's run through all of them. It is isolating each harmonic or near harmonic. It is also calculating the B value for the equation below in the comments. Now, the loudness here is normalized, so these higher order harmonics aren't actually this loud. You can see their relative amplitude over on the left. That is the real sound, and now we are going to play the filtered version. So this is step one of the model. We have successfully decomposed our original sound into, I think it was 10 bands. But we're not done yet. Now we're going to extract the amplitude contours of each one of those bands. And then we will be able to display in a robust model form. This is the average amplitude of each corresponding harmonic or near harmonic. This is the amplitude proportion spectrum, which shows the average amplitude over time with also the corresponding proportion of each near harmonic over time. So this picture right here is really summing everything up. Everything that I just did can be summed up in this picture. We can see average loudness over time. We can see proportion of each harmonic over time. Now we could squish these proportions versus time. We could expand them. We could change the loudness contour. We could pitch shift. Let me show what happens. I could pitch shift this model. In a different video, I'm going to show how this model can also handle speech. Thank you for watching.